Above and below the Milky Way are two gigantic bubbles blasting out gamma rays, the most energetic light in the universe. For 15 years, we've been trying to figure out what created them, and we thought we had the answer, but now new research has just complicated everything. These are the Fermi Bubbles, found by the Fermi Gamma Ray Telescope back in 2010. Two bubbles of gas so hot that they're giving out gamma ray light, 1 billion times more energetic than the light that we can see with our eyes. And for the past 16 years, us astrophysicists have been trying to work out what these bubbles are and what formed them. And at the start of the 2020s, we thought there was finally enough pieces of evidence that have come together to solve the Fermi bubble mystery. But then, at the end of 2025, a new research paper by Sands, Hopkins, and Panada has put the cat amongst the pigeons once again. So in this video, we're gonna dive into this and chat first about how did we find the Fermi bubbles and why are they glowing in gamma rays, then chat about the possible explanations for the Fermi bubbles, and finally, the evidence in support of each of those explanations. But before we chat about the unknown of the Fermi bubbles, you should make sure that you're protected from the unknown of the internet thanks to Surfshark, the sponsor of this week's video. Surfshark is a VPN, a virtual private network, and it's essentially a middleman between your computer and the scary internet, which means that your private information, your location, and whatever you're doing is all hidden from anybody who happens to be snooping. Surfshark is crucial for me as an academic because I'm always working on public Wi-Fi networks, whether that's in the office or in the university library or in airports when I'm traveling for work. I'm planning to use it on my upcoming trip to the Dark Sky Reserve of Joshua Tree National Park. And it'll mean that no one can snoop on either my unreleased research paper that I might be working on in the airport or my credit card information. Plus, Surfshark helps you get the best price when online shopping, so websites usually show you prices based on your location, especially when it comes to flight prices. So Surfshark helps you get the best deals, which means I can make the most out of my very limited research travel budget. I also love that Surfshark has an antivirus software, so it shields my devices from viruses, malware, and ad tracking. Look, there's no risk in trying out Surfshark because they offer a 30-day money-back guarantee. So try them out today, and if you use the code Dr. Becky or click on the link in the description down below, you'll get 4 additional months free on your subscription, which is an incredible deal for you all. So thanks again to Surfshark for sponsoring this video and keeping us all safe online. And now let's dive in and chat first about how did we find the Fermi bubbles and why are they glowing in gamma rays? Because if you look at an image of the entire sky taken with a gamma ray telescope, which is an egg shape because you've taken the inside of a sphere and flattened it down to 2 dimensions, you won't actually be able to spot the Fermi bubbles. Instead, you can see a lot of really bright points of gamma ray light, where you've got high energy objects like supernovae or black holes and pulsars emitting gamma rays that are just scattered around the universe and across the entire sky. And then you've got an incredibly bright strip along the middle. That is our home, our galaxy of stars, the Milky Way. The gamma rays here don't come from individual objects. They come from high energy charged particles colliding with the atoms in gas and dust in the space between stars in the Milky Way, which transfers so much energy to those atoms that they end up releasing that energy as gamma ray light. It's only when we mask out both the bright objects and the glow from the gas and dust in the Milky Way that we then notice the emission from the Fermi bubbles. And it's a very distinct emission too. It has a very different signature to the emission that we see from the gas and dust in the Milky Way. So a very different spread of energies of gamma ray light that the Fermi bubbles are emitting. There are much higher energies than we typically see given off by like the galactic plane of the Milky Way. To produce those high energy gamma rays, what we need are high speed electrons, accelerated to nearly the speed of light before they collide with a low energy photon of light, something like infrared or radio light. That collision slows the electron but adds a load of energy to the photon, producing a gamma ray. This process is known as inverse Compton scattering. And it's why we have very different signatures from the Fermi bubbles to the gas and dust emission from the Milky Way. Another distinguishing feature of the Fermi bubbles is that the edges are really clear. They are sharp-edged rather than fading out, suggesting a sudden release of energy is what caused the Fermi bubbles rather than a slow and gradual process. Not to mention the fact that the Fermi bubbles are absolutely huge. This is an image of the entire sky, and the bubbles cover roughly 10% of that image. They're 50,000 light years long from top to bottom, which is half the width of the entire Milky Way galaxy of 100 billion stars. But it's not just Fermi that spotted the bubbles. In 2013, they were identified as the source of the microwave haze in the foreground of data from the Planck telescope that was mapping the cosmic microwave background, the echo of light from the Big Bang. Then, in 2020, Krishna Rao and collaborators announced they'd managed to detect visible light coming from the bubbles as well, specifically from hydrogen that likes to glow at a very specific colour or wavelength of light. And also in 2020, the recently launched eRosita telescope detected X-ray light also coming from the bubbles. So, given everything we know about the bubbles, what are some possible explanations for the Fermi bubbles? Okay, so we're going to need a process that's able to eject a huge amount of energy and specifically accelerate things like electrons up to incredibly high speeds close to the speed of light. Plus, from the position of the Fermi bubbles, that process needs to have happened towards the centre of the Milky Way galaxy. So there's a couple of ideas that have been raised over the years, but there are two main frontrunners. Either lots of supernovae went off in the centre of our galaxy, or there was a big burst of activity from around the Milky Way's central supermassive black hole. Let's start with the supernovae, because the centre of the Milky Way is incredibly dense. There are a lot more stars there than there are out on the edge of the Milky Way where the solar system and the sun are found. So at some point in the galaxy's history, if there was a big burst of star formation where a lot of stars all formed at the exact same time, the biggest, hottest stars, which lived the shortest lifetimes, would all then have come to the end of their lives and gone supernova at around the same time. That combined effect of lots of supernova in a short space of time effectively sets up a wind away from the centre of the galaxy, ejecting lots of hot gas and also charged particles that have been accelerated in those supernova explosions. But you might be thinking, but supernova are spherical though, with winds blowing out in all directions, not just above and below the Milky Way, like the shape of the bubbles. But the only cumulative effect we'd see is along the path of least resistance, up and out of the galaxy where there are no stars and gas and dust in the way, giving us bubbles above and below the galaxy's flat disk. Now this isn't as crazy as it might initially sound. We've seen similar shock bubbles at much smaller scales, like in the Orion Eridanus superbubble, which is 1,200 light years across. It's a shockwave bubble that formed from overlapping supernova remnants from stars formed in the nebulae we see in the Orion constellation. We've also seen it on these huge galaxy-wide scales as well, like in the galaxy Messier 82. This is a starburst galaxy that overall is 5 times brighter than the Milky Way, but its central regions are 100 times brighter because of that central starburst. And Messier 82 has dusty filaments extending above and below the flat disk of the galaxy that are a result of emissions of heavier elements from supernovae. So we're seeing M82 in its starburst phase now. So was the Milky Way once like this? And if so, are the Fermi bubbles an echo of what's seen in Messier 82? Or are the Fermi bubbles an echo of a past burst of activity from the Milky Way's central supermassive black hole? An area of space with so much stuff, with matter so dense that to escape the pull of its gravity, you would have to be travelling faster than the speed of light. It's 4 million times heavier than the sun in a region of space smaller than Mercury's orbit is wide. Now, while we can't see black holes themselves because the matter and the light all gets trapped there and nothing can escape, we can see materials spiraling around black holes in what's known as the accretion disk, which we can see because the material in it is accelerated to such huge speeds that it gets so hot that it glows. The accretion disk, though, is a very energetic and very chaotic place, though, with immense pressures because of how hot that material in the accretion disk actually is. But that pressure in the accretion disk can get relieved through outflows, either winds that ripple through the galaxy or up and out of the poles in huge jets if the material is funneled there by magnetic fields. And we know that these jets and outflows can also accelerate charged particles up to near the speed of light. Like Messier 87, which has a jet 260,000 light years long. That's twice as big as the galaxy is wide. So we're seeing Messier 87 with an active supermassive black hole now that is actively spewing out a jet from the regions beyond its event horizon in the accretion disk. So was the Milky Way once like this, but now the black hole has quietened down? And if so, are the Fermi bubbles an echo of what's seen in Messier 87? Now, there have been other ideas raised to explain the Fermi bubbles, from dark matter annihilation or cosmic ray acceleration in the Milky Way's halo itself. But like I said, the supernovae and the supermassive black hole explanation are the two main frontrunners, with lots of arguments back and forth in the scientific literature over the 2010s, arguing in favour of one or the other, with some people saying supernovae just don't have enough collective energy to explain the Fermi bubbles, or that the Milky Way's supermassive black hole is very quiet and we just don't have evidence of any past activity. Which brings me finally to the evidence in support of each explanation. Because in the past 5 years, the evidence in support of the supermassive black hole explanation has been slowly growing, with a lot of people, including myself, being pretty convinced that that was the explanation. So in 2021, Pilipik and collaborators published this paper analysing the TNG 50 simulation. This was a big cosmological volume simulation that simulated the evolution of the entire universe. And in it, they found that if they looked at Milky Way-like galaxies after like 14 billion years of the universe's evolution, 2/3 of them had X-ray emitting bubbles, shells, or cavities in the gas above and below the galaxy's disks that were very similar to the bubbles seen by Fermi and E Rosita in X-ray. And the fun thing about simulations is that you can run time backwards to see what actually caused those bubbles. And Pilipik and collaborators found that it was energy output from the region around active supermassive black holes in the centre of these galaxies. And from how common these are in the simulations, Pilipik and collaborators suggest that we should be able to spot these things around other galaxies in the universe with the E Rosita telescope. But as far as I'm aware, nothing has been found just yet. Perhaps they are too faint if they're there. Then a second paper released in 2022 by Yang, Ruskazowski and Zweibel also supported this idea of the supermassive black hole being responsible for the Fermi bubbles. This time they ran simulations of a single galaxy with a supermassive black hole that had jet activity just a few million years ago and could recreate the look of the bubbles as seen in the gamma ray, X-ray and microwave emission. Together, these two papers, released within a year of each other, had me convinced anyway that the Fermi bubbles just had to be explained by past activity of the Milky Way's supermassive black hole. It just made sense. But then, last year, in 2025, this paper by Sands, Hopkins and Panada appeared online claiming they could recreate the bubbles in their simulations with just supernovae activity alone, and nothing from the supermassive black hole. Now, as far as I can tell, this paper hasn't been peer-reviewed yet by colleagues, by fellow scientists, so just take everything I'm about to say with a rather large pinch of salt. But in all three of the Milky Way-like disk galaxies that Sands, Hopkins and Panada simulated, they did not even include a central supermassive black hole at all. And yet they still found bubble-like structures formed above and below the flat galaxy disks that were glowing in gamma rays, specifically from inverse Compton scattering. So now I'm back to not knowing what to think. Perhaps it's possible to get these bubble-like structures from both processes, but that doesn't help us narrow down which one actually forms the Milky Way's Fermi bubbles. But simulations like the ones run by Pilipik, Yang, Sands and collaborators will help make predictions for what we should be able to see across multiple wavelengths of light in each of the different scenarios, supernovae versus supermassive black hole. And maybe we might just then be able to solve the unsolved mystery of the Milky Way's Fermi bubbles. Sorry, my notes currently say the centre of the Milky Way is desert. There are more stars there. I think it's supposed to be dense, not desert. So there's a couple of ideas that have been raised over the years, but there are two main front flubbers. I wore this t-shirt today because it's got all the telescopes on it and it's got Fermi on, but it's like down here in this corner and you can't see it, but it is there. It's over here in this little corner. Hi Fermi. I do love this t-shirt. It's very nerdy, but I love it. It's a sharp edge rather than, rather than, you know, brain fog. Rather than teetering? No, oh my god. Rather than fading out. Oh my god, that took forever.